Hello. In this video, we're going to go over question 7, which is some sampling. Specifically, in the first part, I'm going to go over the Monte Carlo method. Then after that, I will solve the problem using the Monte Carlo method. Okay, so one thing I want to get started on before this was just to really clarify on exactly how we do sampling and why it works. So I'm going to be doing a separate example to sort of demonstrate exactly how this works. Okay, so the Monte Carlo method is a method that takes the idea of the law of large numbers, right? So if you take a ton of numbers, you take 1 million, you take 1 billion samples from a distribution, and take 1 trillion samples from a distribution. The larger and larger you get, the more and more the average of the samples that you get, assuming you took actually random samples, the average of the samples will be the average of the distribution. So the Monte Carlo method uses this rule in order to get a good guess at the integral of a function. So I've drawn out this diagram here, and as you can see, the area under the curve of this diagram, and I've divided it up into squares just to make it very, very clear. But you can see that there's 5 squares, and so the area is 5, right? And specifically, we can see that this area right here is a length of 1. This area up here has a length of 2, and we'll get back to that later. Now, the Monte Carlo method tells us that, and here's the formula for it, b minus a over n multiplied by the sum. That's a bad sigma. By the sum, I equals 1. That's not really much better sigma, but I guess I'll work with it, of f of x sub I, right? And this is where n is the number of samples, b is the upper bound, and a is the lower bound. So this formula may not make a lot of sense intuitively when you look at it, but let me break it down into a different form and maybe it'll make more sense to you. So we take b minus a, and we multiply that by 1 over n, and that is multiplied by our sigma, right? And if you think of it, 1 over n times all of our samples, well, as n goes to infinity, this is going to equal the average of our thing, of our function, right? And we multiply that by b minus a in order to scale it to the length that we're doing, right? So that's really the method behind the Monte Carlo method. So let's now put this into practice. If we look at our thing, I need to stop calling it a thing. We look at our area. We have a segment that is 2 tall, which is of length 2, and we have a segment that is 1 tall, that is of length 1. And so if we take 1 million samples, we could say that there are probably 2 entries that have height 2 in comparison to, for every 1 entry there is of height 1. So the distribution of samples looks like this, right? And that means that the average height of this area is 5 over 3. I'm not going to take 1 million samples on paper because I can't do it, but I think we can all agree that the average f of x here is 5 over 3. Now, if we multiply this, we use this in our Monte Carlo method, we have b minus a over, and then actually I'll use the other form here, 1 over 3 times, and then the sum of all of them, 1 over n times 5 over 3. And if we do this, and this is times n here, because there's n samples, I'm just going to assume that we sample 1 million times, and roughly the average of all the samples is the average, so I'll multiply that by n, divide by n, and if we do all this, well, b is 3, a is 0, we multiply that by 5 over 3 times n over n, this just gives us 5, which is in fact the true area. So I've just shown you that the Monte Carlo method, when you use the true average, it actually gives you the exact integral. But the Monte Carlo method, we're not using the true average. We're just sampling as many times as we can in order to use the law of large numbers, which tells us when you sample a lot, you get really close to the true average. Okay, so hopefully that's clear to you on how the Monte Carlo method works. And now I'm going to actually do the question. So let's just do it. So f of x equals 0.5x plus 2, if I remember, yes. And we know that our samples are 0.2 and 0.3. We know that we are integrating from 0 to 3. So we know that b is 3, a equals 0, and n equals 2 because we have 2 samples here. Now, one catch that we need to really pay attention to. If we read the instructions out loud, maybe you'll find it as well. So the instructions say, when you're sampling from a uniform distribution to approximate the following integral, if you only generated 2 samples of the values 0.2 and 0.3 from a uniform distribution ranged between 0 and 1, what is the estimated solution to the integral using these 2 samples? Now, the catch that I'm trying to convey here is here. We sampled from a uniform distribution between 0 and 1. So we need to scale the samples that we got so that they fit the range of the integral. So we took samples from here, but we are using an integral that's from 0 to 3. So we need to just multiply all of our samples by 3 before we put them into our function, right? So actually what we're going to be doing is this. Okay, so now that that's clear, let's just do the math. We have, let me just erase that. We have 3 minus 0 over 2 times the sum of all f sub xi times 3, which is 3 over 2 times, I believe it's f of 0.6 plus f of 0.9, which gives us 3 over 2 times 2.3, yes, plus 2.45, which is 4.75 times 3 divided by 2, and that would be 2.375 times 3, which is, that's 3/8, so it's 3 over 8 and 2, so it's 7 1/8, right? Yeah, 7 1/8 is our final answer for this problem. Okay, so that's the Monte Carlo method. Hopefully now you know how to do any variants of this problem that we can throw at you because you understand the mechanics, the reasoning, and how to use the Monte Carlo method. This is pretty important for the future, but yeah, that's it. Good luck.